So now that we've understood our goal, the goal is to capture how-to knowledge by breaking problems down into mechanical steps, and then to figure out how to turn that into something that the machine understands, the computer understands, so that it can execute those steps for us. We're ready to start putting those pieces together. In the next lecture, we're going to begin doing that in Python. But before we do, we want to talk about one last piece, about what it means to create recipes. Every programming language provides, as we've said, a set of primitive operations. They're defined ahead of time. They're the components of the ALU that make the computer do its work. So we're going to build on top of those. Similarly, every programming language provides a means or mechanism for combining primitives to form more complex but legal expressions. How do we put together sequences of operations? How do we define the kinds of things that we want to do? And finally, every programming language provides a mechanism or means for assigning a meaning or value to each computation or expression. That's going to let us map between what the computer actually does and what we want it to do. Knowing that a particular expression leads to a particular kind of value is going to allow us to deduce the sequence of operations that we want to use. So, when we talk about programming languages, we need to talk a little bit about the primitives, about how we put them together to make legal expressions or more complex things, and then how the computer is actually going to deduce the value or meaning associated with an expression. That means that when we talk about languages then, we'll start by first describing what are the primitive constructs, what are the elements out of which we put things together. In programming languages, we're going to see that those basic elements are things like numbers, strings or sequences of characters, and simple operators. And in a real language or a natural language, the equivalent is, for example, words in English. What are the words of the programming language? What are the basic units that we put together? When we go to put them together, we will talk about the syntax of the language. And that tells us which strings of characters and symbols constitute well-formed combinations in the language. In programming languages, as we'll see when we get to the specifics, it'll be things like a number followed by an operator followed by a number is a valid Python expression. And it says basically apply that operator to those two numbers to do the right arithmetic thing. That's a well-formed expression in Python. We have the same thing in English. There are words that can be put together in some ways, but not in others. So, for example, in English, the sequence cat, dog, boy is not syntactically valid because it's not in the form of an acceptable sentence. So in programming languages, we'll worry about defining the syntax. How do you put things together? In addition to the syntax, we also have the semantics of a language. And semantics refers to the meanings associated with the expressions. And we're going to make a distinction between two kinds of semantics. First, there's static semantics. That basically tells us which syntactically valid strings, that is, sequences of words that satisfy the syntax of the language, which of those also have a meaning. For example, in English, I are big has the form of a noun, an intransitive verb, and another noun, so it's syntactically valid. It's in the right combination for what would normally be a sentence. But it's not valid English because I is singular and R is plural. So this would violate the static semantics of English as a natural language. In programming languages, we're going to see similar things. For example, having a literal followed by an operator, followed by another literal. And a literal just refers to a number or a string or some other legal combination of things. That literal operator literal is syntactically valid. But, for example, we'll see in Python that 2.3, the slash, and the string ABC is not semantically valid. It's a static semantic error because we can't divide numbers by strings. So again, as we talk about our language, we're going to talk about what are the static semantics of putting things together to create legal expressions. And then finally, there is the formal semantics or full semantics of the language. And that says what's the meaning associated with a syntactically correct string of symbols that does not have any static semantic errors. What's the meaning associated with an expression? Again, we see the differences between natural languages and programming languages. In natural languages, like English, sentences can actually be ambiguous. For example, the phrase, I cannot praise this student too highly, has two different meanings. One can be what you would take on the surface, which is saying, I really like this student. And one can be seen in a somewhat sarcastic manner as basically saying, it is impossible for me to praise this student. The meaning comes from other things, like context or intonation or those kinds of things. So in English, the semantics often is straightforward, but sometimes is interesting. In programming languages, we're going to see that we always have exactly one meaning associated with a legal expression. But we're also going to see that that meaning may at times not be exactly what the programmer intended. And we're going to have to come back to that as we walk our way through determining how to associate appropriate meanings with different expressions. But we will talk about the semantics of a language as we move through building up the expressions. And we'll see that the semantics is what we want. It tells us what is the meaning of an expression. And we're going to want to work backwards from that semantics to deduce the right syntax to capture the primitive operations to get us to that meaning. When we have these different pieces, we can also think about, so what can go wrong? What can have things actually cause problems in the system? And we'll see that we can get errors or bugs, as we're sometimes called, in all of the different parts of a language. Syntactic errors are quite common, but they're also easily caught by the computer. It's pretty straightforward in a modern programming system to write an operating system or an interpreter that can actually check for syntactic errors before you try and run the program. And good systems will not only catch them before you run the program, they'll also point you to the place and provide you with suggestions as to what you need to fix in order to make the program syntactically correct. So static semantic errors do occur, perhaps not as often as syntactic ones. Some languages are very good at actually carefully checking ahead of time to catch these errors before running the programs. Others are caught while you're actually interpreting the program. Or another way of saying that is in what are called compiled languages, as we'll see, the system will work hard to catch these errors before you ever get a chance to try and execute the program. In languages like Python that are interpreted, we'll see that the program will walk through executing, or the interpreter rather, will walk through executing the whole program, and on the fly will try and spot possible static semantic errors and alert us at that time. One of the downsides is it is sometimes a little harder to debug the programs because you're only getting to the error when it occurs, and you have to work backwards to figure out what caused you to get to that place. Finally, as we suggested, programs don't have semantic errors in the sense that there is a meaning associated with the program if it is syntactically and statically correct. But the meaning may not be what was intended. And so what are common problems? The program crashes, or said a little less bluntly, stops running. That's because we made an error of some sort that causes a problem inside of the machine. The program runs forever, or at least until we get tired of it and hit a particular command to stop it from running, because it's entered, for example, into an infinite loop. Or perhaps the most troubling is that the program may actually produce an answer, but it's not what we intended. And we're going to talk throughout the term about how to guard against those kinds of errors by practicing things that we call defensive programming. So, let's pull this together then. Our goal is we want to learn the syntax and semantics of a programming language. Those are the details of both how to construct legal programs and get them to do interesting things. But what we really want to do is to learn how to use those elements to translate our recipes for solving a problem into a form that the computer can use to actually do the work for us. We want the computer to compute answers to interesting problems. We want to provide the algorithm, the sequence of steps that's going to make that happen. And we want to do that by building off of the syntax and semantics of our programming language. And stitched together throughout this is going to be this idea that to make this really work, we need to come up with smart ways of capturing the computation. So that computational mode of thinking, that way of taking a problem description and breaking it down into a recipe, a sequence of how-to steps, is going to be really valuable. And throughout this course, we're going to build up a suite of tools to let us do that. In the next lecture, we're going to start doing all of these pieces.